An ideal P is prime if P contains two other ideals, A and B. Then it must contain one or two. And let me also point out that my definition of prime and maximal won't be to be proper ideals. Okay, so the last thing we had, theorem. If is an ideal with property that A times B is in P and plus A or B is in P.
Hi, are there any extra masks in here by chance?
Sorry,
Across the hall.
Oh, yeah.
with the property that and R is commutative in complex. That is to say, if you have a commutative ring, then this property here, the product of two elements being in P implies one of the two elements must be in P is characterized. Okay, so let's get the first statement first. So suppose P is an ideal property that A, B is in P plus A and B are P. So suppose P has this property. To show P is prime, I just have to show that. So to this end, let's assume that let's suppose that the ideal A is not contained in P. So it's our burden to show that B is in P. Then we select an element A that is in so if A is not contained in P, I can certainly select an element A that's in A, not P. Note that B is contained in P. And right, because in particular, any A times anything in B is certainly in that set, so it's contained in B. So for all B and B, A times B is in. But we have this problem. So for all B and B, A, B, and P, but since A is not in that, therefore, every element of B is in fact in B. Now suppose so what we've shown so far is any ideal with this property is prime. Now we want to show in the commutative case that if you have a prime ideal, then it's got that property. I'll suppose that the product of two elements, A times B, is in P. Well, so the ideal, sorry about A, B. And so read this, the commutative part. Since P prime, the ideal generated by A is conveyed in P, or the ideal generated by P. Therefore, A is in P. So look through that and see where we use community. Okay. All right. So let me give you another lemma, which is actually going to lead to a definition and a generalization of prime. So here's the following lemma: 5, 3, 5. R be commutative and I an ideal. By the way, throughout all this, you can assume that R has a 1 unless I specifically tell you otherwise. One. My default is green will have 1 unless I specify otherwise. And R. We can find for the set the definition of this. This ideal is called the radical of I. Let me mark. I is contained in the radical of I. Because what the radical of I is it's the collection of everything that a big enough power blasts back down into the ideal. In particular, notice that I itself, notice that any element of I is in the radical because if it's already an I, then you can just take n to be the first power. Right? So as a set, the ideal I is contained in the radical I. Why is this an ideal? Well, because that's what it means to live and practical. notes. And this might be some work on the homework. No. If you look at this power of x plus y, x. Now notice that if minus k is at least n. Is at least n, then what we're saying here is this exponent here is at least n, and x to the n is 9. So any power exponent is 9. Yes,
Did you mean to say at the beginning that X, Y are in the radical of I?
I did. Okay, so everybody with me so far. So if the exponent of this is at least n, then this term is sucked into I. If that, let's stick the mouse away here, that m is what means k is greater than or equal to. Because now the exponent here is greater than or equal to. So what we proved is in this expansion, either that exponent is at least n, in which case the power of x is big enough to be an I, or the exponent is less than or equal to n minus 1, in which case the power of y gets you n. So x plus y, n plus n minus 1 is an I. So x plus y is in bracket of I. I will leave as an exercise the proof that this is a vacuum cleaner. That's actually pretty easy to see, because if Rx is in, if X is in radical I, then if you look at Rx and take a big enough power of that, then that's also in. Radical ideals are very important, and we'll see how so in just a moment, or we'll see one of the reasons. Definition. Five, 3, 6. But R 1. We say the ideal I and R is number 1. Radical. I is equal to its own radical. So that is, it already contains everything that an nth power will put it in there. And 2, primary. A, B, and I implies A is an I, or B to the N is an I. By the way, these are both generalizations of prime ideals. let me point out that any prime ideal is radical, because if x to the n is in the ideal, and it's prime, then inductively you can show that x is in there. And primary is maybe a clearer sort of generalization, because prime is primary for n equals 1. Right? So here is one of the reasons why we care about these types of ideals. And I'm not going to prove all of this, but I'll prove some of it. I think if I prove like 1 or 2 of these, we'll get the gist of it. Those are these commutative. And R is an ideal. Number 1. Maximal. You might want to guess this one. What's that?
Prime ideal?
Well, so yes, any maximal ideal is prime, but what I'm saying is I is maximal. What does that mean about the structure of R mod I? R mod I is very, maximal ideals make this have a very nice structure. Take a guess. I'm sure you won't be too far afield. There you go. That's a cool result. Number 2, I and R is prime. If and only R mod I is domain. By the way, let me point out something. With this characterization here, it makes it pretty obvious that maximal implies prime, because any field has to be an equal element. Number 3, I and R is radical if and only if R mod I is reduced. And I haven't told you what that means yet, but that means no non-zero nilpotents. So the ring is reduced if the only nilpotent element is 0. And 4, I and R is primary if and only if every 0 R mod I is nilpotent. This one's sort of the opposite. What this one says is every 0. Okay. Let me prove a couple of these just for fun. Like, let's be odd about it. Prove 1 and 3. And I think that if you see what I do for 1 and 3, you'll get the gist of how the rest of this works out. Number 1. You know, actually, one year at North Dakota State, when I was there, we had somebody writing a master's thesis in commutative algebra, and they did a lot of stuff with ideals. And so they had this really long thesis and all this results about I being a maximal ideal and stuff. And so we had to back then send our thesis to, they had somebody that corrected the thesis over in the graduate school, somebody out of the English department, languages or whatever. We'll go through this. And so there are all these statements in the student's thesis that said things like, suppose I is maximal. We got 150 changes like that. So a little knowledge is a dangerous thing.
They thought that the student was writing, I am maximal.
That's exactly what they thought. So let's suppose that I is maximal. What we want to do is show that R mod I is a field. So R mod I suffices to show any non-zero coset as an inverse. Right? Because that's really what we need here is we need every non-zero element of R mod I, that is any non-zero coset, to have a multiplicative inverse, right? So suppose I have a non-zero coset A plus I. This means that A is not an I. That's equivalent to saying coset's non-zero. And so, since A is not an I, and I is maximal, let me recall for you what this means. This means the smallest ideal that contains all of I and also A. Now, A is not in here. So this is honest to goodness bigger. Right? And since I is maximal, if it's honest to goodness bigger, it has to be all of R. Everybody okie dokie so far? So there exists I and R and R such that because one lives in here, and so one lives in here, and what does a typical element of I comma A look like? When we talk about all these generators, what it looks like is it's an element of I plus something in the ideal term by A, so it's a multiple of A, and hence the RA. Everybody okay? Notice that notice that RA minus 1 is, well, I got my sign on there, negative I, which is an I. Therefore, the coset RA plus I equals 1 plus I. But this is the coset R plus I, A plus I, and here is the inverse. So R mod I. Any questions? Go the other direction. Suppose R mod I is a field. I'll let now if I is maximal, which I hope, we need to show that N is the entire room, right? Because we're assuming that R mod I is a field. Our basic strategy is to show that I must be a maximal ideal. So let's suppose that there's another ideal that contains it. And our goal here is we were going to show that this animal is in fact all of ours. And to that end, I'm going to show that there's a one. Since I strictly contains n, there is this x, and it's not an I. So the code says x plus I not equal to 0 plus I, and so has inverse I plus I. That is to say, x plus I and y plus I plus y plus I. So what does this mean? Well, this means that there is a y r such that xy minus 1 equals I. Or equivalently, y minus I. Now, how does that help us? Note xy minus I, then the ideal generated by I and x, right? Because notice that I is an I, and x times y is in the ideal generated by x because it's a vacuum cleaner. And this is contained in n. Because I is contained in n, and x is contained in n. Therefore, 1 is contained in n because x minus I y is 1. So R and I. And I think I'll just do one direction and the other one. Let's do 3. Any questions so far? Let's suppose that I and R is radical. Let me kind of briefly debrief on what this means. This means that x to the n is I and not I. Right? Because the radical is the set of everything whose power, beta powers in I, but it's a radical ideal, so it already contains it. All we have to do now is show that R mod I is reduced. We need to show that there aren't any non-zero nilpotents. That's what it means for this coset to be nilpotent. And this is how you multiply. Therefore, x to the n is an I. Implies that x is an I. Because we now use the radical part. Therefore, x plus I equals 0 plus I and R mod I. Any questions on that? I encourage you to work through some of these others. These are all kind of similar. And it's a good exercise in sort of familiarizing yourself with these problems. Okay. Let me give you a corollary to this, because I can't resist. Any maximal ideal is prime. By the way, the proof of this, the direct proof of this, any maximal ideal is prime is not very difficult. So think about that too. But it rips off from this really easily because any field is an integral domain. Bang. So maximal implies prime. I love that. And also, I is prime if and only if I is both radical and prime. Because if you have an integral domain, it's certainly reduced because, in fact, the only zero divisor at all is zero. And this statement is also true because there aren't any zero divisors other than zero in an integral domain. And you can work it backwards as well. Okay, let me give you one more corollary. Because I can't resist it. This is actually important in something called primary decomposition, which you probably won't have time to go through in this course. Okay. So what this result says is if you have a primary ideal, the radical of the primary ideal is prime. You can do this as a corollary to theorem 537. I'm just going to do a direct proof here. Suppose to show that J is prime, then I need to show that either A is J or V is in J. Since J is the radical of I, then a big enough power of AB has to push AB back down into I. So think of this as a product of two things. And remember, my assumption is this is primary. Let's note first, if AN is an I, then A is in radical I. And if not, then there exists K in the natural numbers such that need to be done with K is in. But again, B is in the radical of I. So A is in I, or I'm sorry, that's J. So it's any questions? Okay. Now, I'm fixing to do a central, absolutely central theorem of the valve. This is one of the daddy max, if you will, of the valve, one of the real big cogs in the wheel. It depends on something called the axiom of choice. How many of you have heard of this, right? I mean, it's Halloween. You probably heard stuff around the campfire about the axiom of choice last night, right? So the axiom of choice is basically, it says very fast and loose. If I have an arbitrary collection of sets, I got a choice function. That is to say, I can go through and I can pick whatever element I want out of the set. This is equivalent to the statement that if I have a Cartesian product of any collection of non-empty sets, then that product is mine, right? Pretty obvious, right? There are some wacky things that can happen as a consequence of the axiom of choice. But I'm here to tell you that the good outweighs the bad. And when it comes to mathematics, or when it comes to commuted algebra, pretty much all working mathematicians are pro-choice in that sense. So here is how many of you have heard of Zorn's Lemma? Right, maybe you don't remember what it is, but another maybe heard of the focal. Right? Zorn's Lemma is the consequence of the axiom of choice that we need. Well, it's really useful in community valve. So let me make a statement of that instead of the axiom of choice. Let S be a partially ordered set. So you have some relation where you might be able to compare two things, right? So do y'all remember what partial ordering is? It's a way to compare two things. Now, it behaves the way you want. If A is less than or equal to B and B is less than or equal to C, then A and B have to be the same thing, right? Less than or equal in both directions. You want it to be, you want everything to compare to itself. That is, A is less than or equal to A. And you want transitivity. If A is less than or equal to B, B is less than or equal to C, then A is less than or equal to C. Now, what the descriptor partially, what the adverb partially here means is you may not have all apples in the basket, right? If you pull out two apples, you can compare it. But you might pull out an apple and an orange, there's no way to compare it, right? So partial ordering means that all those things apply only if you can actually compare them. So suppose you got one of these things. And here's a good example to keep in mind is the collection of subsets of the set, because some of them contain each other and some of them don't. Right? Every chain. Let me mind what this means. Total subset. So in other words, when I got a chain, that means I pull all apples out of the basket, or all oranges. So a chain is totally ordered, means you can compare everything in the subset. So here's the situation. You have a partially ordered set, call it S. You might have apples and oranges in there that you can't compare, but this set has the property that if you ever pull out all apples, that is any chain, then this has, so you pull out all these apples that you compare, then this subset has a maximal or has a upper bound in S. Then the set S must have a maximal element. Do not try to prove this. It's equivalent to the axiom of choice, and so it's hopeless. So this is just like the axiom of choice, but we're going to use this. Here. 310. Almost. Let's take correct with that R. And on proper and I is contained. Maximal. So in 3, 1, maximal. I can remove the word left. Any ring has a maximal left ideal. It also has a maximal ideal. It's got a maximal right ideal. The proofs are all the same in this. Let me prove this first statement here, which is a little bit stronger. If you have a ring with 1, then any proper and I and R is a proper left ideal, then it's contained in the maximal. So here we have our proper ideal. Now, Jim is now going to build a partially ordered set, just like I will use from Zorn's Lemma here. And here's my partially ordered set. My partially ordered set, I am just going to gather together the collection of every single ideal, or left ideal, if you will, in R that contains I. And my partial ordering my conclusion. Now, let me point out that this could be a partially ordered set because you might have I is contained in some other ideal I1, some other ideal I2 that are both proper, but notice I1 and I2 are comparable in this case. But some ideals might be, like this one, I3. I3 and I1 are comparable, but I3 and I2 are not. Okie dokie so far. Now, by the way, I should probably sit here and make sure that I'm not doing some kind of fancy computation on the empty set. Somebody tell me why this is not empty. That's right. I is certainly an ideal that contains I and is proper, so no problem there. Now, what we have to do is show that every chain has an upper bound. I'll do some things to set the chain. And what do I mean by a chain? Let me reiterate. So it means if I pull any two random ideals out of this bushel of apples, one of them contains the other. Any ideas what I could do to select an upper bound for this chain? Is an upper bound. Or chain. Because clearly U contains every one of these I alphas, so it's bigger than or equal to, with regard to inclusion, all this. It only remains, so let me put this, if U is in gamma, that is to say, U is a proper ideal. So if you take the union of this whole mass, that's certainly going to be greater than or equal to every idea. It's going to contain all of them. If I can prove that it's a proper ideal that contains I. Number one, I alpha contains I called alpha. So I contains U. I've got that. Two, U is an ideal or a left ideal. And this is precisely true because the fact that it's a chain. If X and Y are in U, then there exists alpha beta such that X is in alpha, Y is in I beta. Everybody okay with that? Now, usually, unions of ideals are not ideals, but here we win. Without loss of generality, suppose that I alpha is contained in I beta, then X and Y are both in I beta. Because this is in I alpha, which is in I beta, and this is in I beta. So X minus Y is in I beta, which is in, and that's really all you need, because the fact that it's a wet vacuum cleaner is pretty clear. And let me make one more remark. I'll let you stew on this a little bit. Can anybody explain why U is proper ideal? We need that too. I mean, it occurs to me, you could blow up and do the whole ring. Notice that one is not in U. That's why it's important the ring has a one. How do I know one is not in U? Because if one is in U, then it's in one of these things. And that would mean that whichever alpha it's in is not proper, which would be a contradiction. So the ideal U must be proper because it doesn't contain the identity. And there you go. Apply Zorn's lemma, since every chain has an upper bound, and you have a maximal element. That is a maximal ideal that contains the ideal I. And we will talk more about this next time. Any questions here or out there? All right. Well, if not, y'all have a good one, and we will catch you on the flip side.